Hello, everybody. Good morning. Welcome to this EGPGV session on flow. This is the second session of this workshop. My name is Holger Theisel. I have the pleasure to chair the session. And we have three very interesting papers about flows and different aspects of flows. The first paper has an interesting abbreviation, HyLiPoD, parallel particle advection via a hybrid of Lifeline scheduling and parallelization over data. And the authors are Roba, Binyahib, David Pugmire, and Hank Childs. And Roba is giving this pre-recorded presentation. And after this, she will be ready to answer your question. Let's get started.
My name is Roba Binyahib, and in this talk, I will be presenting our paper, HyLiPoD, a parallel particle advection via a hybrid of Lifeline scheduling and parallelization over data. This is the outline for my talk, and I'll start by giving an overview of the paper. The performance of parallel particle advection algorithms can vary depending on the workload. In this paper, we build a new algorithm based on the results from a previous bake-off study. In our previous study, we compared different parallel particle advection algorithms to get an understanding of how these algorithms perform relative to each other on various workloads. In this paper, we take the lessons we learned from our previous study and we propose a meta-algorithm that is a hybrid of the two algorithms that had the best performance in the previous study. And to study the efficiency of our algorithm, we compare it with different parallel particle advection algorithms. Next, I'll give a brief overview of particle advection. Advection is the process of displacing a massless particle along a flow from the seed location to the final location in advection steps, which result in an integral curve that represent the trajectory of the particle. Particle advection is the foundation of many flow visualization techniques. Two of these techniques are FTLE and stream surfaces. FTLE is a technique to study transparent behaviors in unsteady flow, while stream surfaces is a union of streamlines connected to form a surface. Different flow visualization techniques have different workloads. For example, in streamlines there are usually tens of particles, each one of them advect for a long duration. While in stream surfaces, there are usually thousands of particles that advect for a medium duration. And in FTLE, there are usually billions of particles that advect for a short duration. These are just three examples, and there are additional workloads from other flow visualization techniques. So we can see that there are usually billions or trillions of steps to compute. So how do we do this? We use parallelization and take advantage of the additional resources to do such heavy computation. Now, if the data is small, parallelization is easy. We can duplicate the data on all the nodes and distribute particles across nodes, and each node will do its computations. But if the data is large, this becomes more challenging. Since we have a lot of computation and the data is large, which means we need to split it across multiple nodes. We need to make sure to have the right data block and the right particle at the same node at the same time to be able to compute one advection step. There are two main algorithms to do parallel particle advection: parallelize over data and parallelize over particles. Other solutions have been proposed as an extension of one of these or as a hybrid of the two. How do these main algorithms work? The first algorithm is parallelize over data, and in this algorithm, we distribute the data between the different nodes, and each node advects the particles located in its data block. For example, node 2 is responsible for the green data block here, which means it will only advect particles in that block. Once a particle leaves the block, it is communicated to the node responsible for the new block. The second main algorithm is parallelize over particles. In this algorithm, the seeds are distributed equally between the different nodes, and each node advects its particles and load data blocks as needed. For example, node 2 will be responsible for advecting these particles regardless of their data block. The reason there are multiple parallel particle advection solutions is because particle advection performance varies depending on the workload. The workload is defined by different factors, such as the number of particles, the seeding box, the duration of each particle, and so on. And different parallel algorithms behave differently for each workload. For example, this workload have a density distribution, where all particles are located in one data block. If the parallelize over data algorithm is used here, the algorithm will suffer from load imbalance, since there is one node doing all the work while others are idle. In the second example, the workload has a circular field. There are 4 data blocks here. Let's say that the cache can only hold 2 data blocks. If we use the parallelize over particles algorithm, this will result in high I/O, since the algorithm will keep accessing the disk to load the same data blocks over and over. The motivation of this work is to create a meta algorithm that changes its behavior depending on the workload to get the best performance while avoiding high overhead. This work built off the results of a previous study where we evaluated and compared 4 of the most popular parallel particle advection algorithms on different workloads. Our study answered different research questions. One of them focused on identifying the best algorithm for a specific workload. The results of the study showed 2 parallel particle advection algorithms that performed best. In this paper, we propose a hybrid algorithm that chooses between the 2 best algorithms to get the best possible performance. To evaluate the efficiency of our algorithm, we compare it with 4 parallel particle advection algorithms. The algorithms we compare to are parallelize over data, parallelize over particles, which I explained in the previous slides, the work requesting algorithm, which is an extension of parallelize over particles, the master worker algorithm, which is a hybrid of parallelize over data and parallelize over particles. These are the abbreviations we will use for the algorithms. POD is parallelize over data, POP is parallelize over particles, LSM is the work requesting algorithm using the Lifeline scheduling method, MW is the master worker algorithm. So how does our algorithm work? To design our algorithm, we use the lessons learned from our previous study to get the best possible performance for a specific workload, which was one of the questions that the study answered. The results showed that the size of the seeding box is a major factor. The seeding box determines if the seed distribution is uniform or dense. The results showed that for a large seeding box, where the seeding box covers the entire domain, POD had the best performance. For a mid-seeding box, where the seeding box covers around 50% of the domain, LSM had the best performance. Finally, for a small seeding box where the seeding box covers around 10% of the domain, LSM also had the best performance. In this paper, we propose a meta-algorithm that is a hybrid between the 2 best algorithms, which are LSM and POD. And we call this algorithm HyLiPoD. We compare the performance of HyLiPoD with the performance of the 4 algorithms, POD, POP, LSM, and MW. HyLiPoD starts by calculating the percentage of blocks included in the seeding box to the total number of blocks, and then it compares the percentage with a given threshold. Depending on that comparison, the algorithm chooses either to behave like pod or behave like LSM. For our experiment setting, the study have 3 phases. The first phase focuses on selecting the best threshold that determines the behavior of the algorithm depending on the size of the seeding box. The second phase studies the performance of HyLiPoD, and the third phase compares the performance of HyLiPoD with the performance of the 4 algorithms. For the first phase, we study 3 different data sets and 10 seeding box sizes. The datasets we considered for the first phase are Fish Tank, Fusion, and Astro. We considered 10 seeding box starting from 10% all the way to 100%. For the second and third phase, we have 6 total number of advection steps, 3 concurrencies, and 3 seeding box sizes. The total number of advection steps is computed by multiplying the number of particles by the advection steps of each particle. We consider 3 options for the number of particles and 2 for the advection steps per particle, resulting in 6 options. We consider 3 concurrencies, and for each concurrency, we increase the number of nodes, the size of the data, and the number of particles. So we are performing a weak scaling study. For the seeding box size, we consider 3 options: large, which covers the entire domain; medium, which covers around 50% of the domain; and small, which covers 10% of the domain. In total, we have 54 configurations, and the total number of experiments is 270. Next, I'll show some of the results of our paper. In phase 1 of our study, we focused on selecting the best threshold. In this figure, the x-axis shows the different sizes of the seeding box, and the y-axis shows the execution time in seconds. When the value on the y-axis is lower, that means the performance is better. The 3 different colors represent different datasets, and the lines with the circles show the performance of pod, while the lines with the triangles shows the performance of LSM. From this figure, we can see that LSM performs better for workloads that have seeding box sizes under 70%, while pod performs better for workloads that have seeding box sizes equal or higher than 70%. So the best threshold for our study is 70%. This means if the seeding box covers 70% of the domain or more, then the algorithm will behave like pod. But if the seeding box covered less than 70% of the domain, then the algorithm will behave like LSM. Now, after we chose the best threshold, we study the performance of HyLiPoD in phase 2. Since HyLiPoD delivers the best algorithm for a given workload, its overall performance informs future research for our community. The figure has 6 particle advection workloads represented on the x-axis, and the y-axis is showing the execution time in seconds. The different colors represent different seeding box sizes. For each of the workloads, we studied 3 concurrencies represented by different circle sizes. From the results, we can see that the algorithm is not scaling well. For example, if we look at the smallest workload, and in particular the mid box case, we see that there is a 10x increase in execution time between the smallest and the largest concurrency. And since we are performing a weak scaling study, the performance should stay constant. In the third phase, we evaluate the efficiency of our algorithm by comparing it to the 4 algorithms. In the figure, there are 4 subfigures. Each subfigure is representing the comparison with one of the 4 algorithms. For example, this subfigure is showing the difference in performance between POD and HyLiPoD. The numbers in the squares represent the execution time of POD over the execution time of HyLiPoD. If that number is equal to 1, it means they have the same performance. There are different findings from this phase. The first one is that HyLiPoD shows improvement over all the 4 algorithms. And this improvement varies greatly over the different algorithms. For each of the 4 algorithms, we calculated an average speedup. These average speedups are as follows: 6.6 speedup over POD, 1.2 speedup over LSM, 1.4 speedup over POP, and 2.8 speedup over MW. The second finding is that we see that our choice focusing on only 2 algorithms was mostly good. While POP outperforms HyLiPods in few cases, due to the extra communication and sometimes extra I/O that HyLiPod performs, since it dynamically balances the workload through work stealing. That being said, the performance differences between HyLiPod and POP were very small and they disappear at higher concurrency. Finally, the third finding is that since MW adapts its execution dynamically, it avoids doing as poorly as POD for mid and small boxes, especially for high concurrencies. But because of the communication overhead, it does not outperform LSM or POP in these workloads. This shows that MW algorithm might be promising if we decrease the communication overhead. To conclude this talk, this paper introduced HyLiPoD and demonstrated that its performance is equal or better than 4 existing algorithms. Going forward, we believe that the meta-algorithm approach is a good way to design new algorithms, which allows us to leverage the strength of different algorithms. For future work, since this work focused on steady state, we would like to study the performance of our algorithm on unsteady state. We would also like to study the impact of different oracles on the performance of our algorithm, as well as adding techniques to adjust the parallelization algorithm used during runtime. I would like to thank my co-authors and all the funding resources that funded this project. Thank you.
Thank you very much, Roba. We are back from pre-recorded to live. And as you can see, Roba is live and here, and she is ready and able to answer your questions. Meanwhile, we are waiting for questions. Let me get started with a question. You had this wonderful curve where you wanted to find out at which points it's better to switch between LSM and POD. You had this sweet spot of 70%. I was surprised that for the 3 different data sets, all the curves look pretty much consistent. And I was wondering, is it because the data sets were so similar in a certain sense, or is it just something that is behind the data set? It's something, a general property independently of the choice of the data sets.
So I do think the dataset has some effect in general on what is the best spot for that threshold. But I think because for our experiment or for Oracle, we chose, for example, similar setting, the same machine, the same number of seeds, the same advection step size. So I think if we changed that Oracle and went to different advection steps or change the size of the advection step, that might change. And the 3 datasets weren't in how they look, they weren't exactly similar. So one of them had a circular field, the other one had a sink, and so they were kind of different. But I think there were some similarities in our or like experiment setting that made that threshold the same for the three data sets.
Okay. All these three data sets, as far as I remember, are steady flow, static data sets, right?
Correct.
Would it change things or the situation, or probably the 70% if we think about unsteady flows?
Yes, so I think it would. I mean, we focused on this study on steady state, and I think still like some of the lessons we took from steady state we can apply to unsteady state. But I think, for example, for unsteady state, your seating position changes from one time step to another, so that will change the behavior of of the algorithm and the performance. So you can start, for example, by uniform seating, and then somehow in the fifth or sixth or 100th time step, the seating changes into dense seating distribution. So I do think it will change, and I do think it will be interesting in the future to look and see what is the impact of that on the algorithm.
Right, thank you. I do not see further questions coming up at the moment. So let's thank Roba again for the presentation. I clap my hand, probably other people do as well. And thanks again. And we come to the second presentation. And the second paper is called all right, here we are again. This is the second presentation, the second paper in this session. And this paper is called Machine Learning-Based Auto-Tuning for Parallel Particle Advection. And the authors are Sam Schwartz, Hank Childs, and David Pugmire. And Sam is going to give the presentation. And after this, we are together here in the room and he's going to ask questions. Let's get started.
I'm so excited to be sharing my research with you today. Particle advection is a fundamental visualization algorithm where we take an individual particle, typically a massless particle, and we go and displace it through a vector field. This visualization algorithm is really important in a high-performance computing context. And typically the underlying vector field is really, really large. We can't actually, place it in just one compute node. And so we have to figure out how to partition it or decompose it into different blocks. So this makes parallel processing in particular difficult, because what we have to do is when we have one particle or really many particles, we have to bring these many particles that we're displacing through this vector field or advecting through this vector field together with the data in order to perform a single advection step. So there's a couple of different approaches that have been constructed to deal with this problem. And the one that we're going to consider is one called Parallelize-Over-Data. And the idea is that the data itself is going to be partitioned across these compute nodes, and then we're going to move the particles between these compute nodes as they move from block to block. So within this particular approach called POD, Parallelize-Over-Data, there are still a lot of configuration decisions that one needs to make independent of the flow field. So there are two decisions in particular that we're investigating in this work, which we think have a significant impact on the performance of our Parallelize-Over-Data advection algorithm. The first is which is, how much data are we giving to the GPU, which is performing these calculations at a particular at once. And the second thing that we're going to consider is the frequency of communication of particles as they move from block to block. Whether we want to aggregate a bunch of small messages at once and wait and send them as a batch, or if we should just immediately, when a particle moves from one block to another, immediately send that communication message. And there are pros and cons to doing that, and I think that it might have an impact on performance. So our big challenge is it's not necessarily clear how we can select these settings in order to optimize performance at the end of the day. This algorithm has some default values which actually perform pretty well, but we think that we can do better. So to do that, we did some preliminary investigation. We took a whole a number of different particle advection configurations. We tried a different number of particles with a number of advection steps, seeding strategy. So are we going to seed a bunch of particles in one area? Are we going to distribute them more evenly across our vector field or our flow field? And then different underlying flow fields to consider in the first place. So we then also did a cross product with a number of algorithm configurations, whether we're going to use this delay send or delay sending of messages at once, and then a number of batch sizes for work that we could put on our GPUs. And so the result of doing this is that we came up with a set of about 2,500 data points where we were able to say, what's happening with our non-default configurations, and then comparing them at the same time with the default settings for this Parallelize-Over-Data algorithm. They were run on Summit, a supercomputer at Oak Ridge National Laboratory in Oak Ridge, Tennessee, the United States. And as a consequence of this, we were able to develop some research questions. The first of which was, well, can we maybe use machine learning to somehow model this behavior, which was not necessarily intuitive at first glance, in order to model the performance of this Parallelize-Over-Data particle advection algorithm. The second research question that we wanted to investigate is if we can somehow apply machine learning to an auto tuning approach, how much speed up could we get? And are we able to somehow compare it to theoretically optimal settings? And what does that mean to analyze that? So to answer these research questions, we considered a two-phase approach. The first phase of our approach is that we were going to train a machine learning model to try to capture the underlying performance behavior of our Parallelize-Over-Data particle advection algorithm. The second thing that we wanted to do is we wanted to then incorporate this trained machine learning model, acting in some ways as a surrogate model, which could then inform the engine of an oracle. And the motivation behind this oracle is that it's going to spit out parameters which will ultimately optimize for speed up given a particular workload. So to be a little bit more specific, what we wanted to do is take this, take performance data, and we didn't want to try just one machine learning technique, but rather we wanted to try a number of machine learning techniques. But in each case, we wanted to play with how we are articulating the data to these machine learning techniques. So a feature engineering, or we're tinkering with maybe taking the natural log of some of these input features derived from our raw performance data, and then hyperparameter tuning of the machine learning technique, and then coming up with a candidate model and trying to assess it to see, is it any good or not? And so the next thing that we wanted to do is, once we had a model that we thought was good, we would go and incorporate it into an oracle of some sort, where the oracle would, the crux of it is that we would, instead of trying to run a number of simulations over on Summit or any other supercomputer, we would run these simulations on the machine learning technique and use that as a surrogate model to try to get a sense of what our performance could be. The outcome being, ultimately, what are the best settings that we can use in order to optimize speedups over the existing defaults. So within that, we tried a number of machine learning techniques. We tried 3 different neural networks. We just called them A, B, and C. These were pretty straightforward neural networks. They were fully connected, variations on fully connected feed-forward neural networks. We just changed the number of layers and the size of these layers, but they weren't particularly complicated. We also tried linear regression just to see, what is something as simple as linear regression do. We tried random forest, support vector machine, k nearest neighbors, and ultimately, once we amass, these numbers of machine learning techniques and selected the ones that we thought were best, we would then plug them into not just one oracle, but 2 oracles. Now, the motivation for both of our oracles is the idea that we're going to iterate a bunch of times over our machine learning model, and then we're going to store the results in a lookup table so that we can have really quick really quick lookup times. And it's pretty simple. It's if our speed up given a particular workload has some algorithm characteristics, and we're going to say that the predicted algorithm characteristics are better than we had before, we're going to return our proposed algorithm characteristics. Otherwise, we'll stick with the existing defaults. So the second oracle is a variation on that with a little bit more finessing of our criteria when we wanted to use ours versus the existing default. But that's kind of the motivation underlying the oracle. So we wanted to figure out how can we do some assessment of this technique. So for the machine learning techniques, we went with k-fold validation, and the idea behind that is, in particular, it was 10-fold validation. We partitioned our training data into 10 different random partitions. We trained on 90% of the data, and then tested on 10% of the data, and then iterated through that 10 times over, and then aggregated our results. So in terms of our oracles, which, that's really where the rubber meets the road, is making sure that the outputs of our oracles work. We ran 108 different experiments. So these experiments were run twice. The first is with the default settings. And then the next time we said, okay, well, what does our oracle say for a particular workload associated with one of these 108 experiments? And the set of experiments that we considered for validation was a cross product of some workload factors. So we tried a range of the number of particles that we were vecting. We tried different numbers of steps within the timeline of the simulation. We tried our 2 different seeding strategies. We had 3 different data sets. And the combination, the cross product of these ended up being 108 experiments. So here's our results. In terms of kind of our phase 1, that is specifically with our machine learning techniques, we actually went and did a little bit more and separated our corpus of training data into two components. The first is that we ideally didn't want to rely too much on our underlying flow field, or minimize the amount of information. So in our training data, we had all these characteristics, but we didn't tell directly to the machine learning algorithms anything about our underlying flow field, and we called that flow field agnostic. We also said, well, maybe understanding or having a clue about the underlying flow field would be helpful. And in that case, for each of our data sets, we said, we just gave it a label. Is this data set A? Yes or no? Is it data set B? Yes or no? That sort of thing. But when we did that, we call that flow field sensitive. So within our 14 different models, 7 for flow field agnostic and 7 for flow field sensitive, we were able to get some results. We measured on one hand, our mean absolute error. How did we get given the predicted amount, how well did we do compared to ground truth as kind of an absolute value. And then we also did compare to unexplained variance. Unexplained variance is really similar to R-squared, if you're familiar with that. And it's just a statistical term to try to get an intuitive sense of how well are our models explaining the data independent of the accuracy as kind of measured by this mean absolute error. For our purposes, the points closer to 0, 0 are best. We want to have no error, and we don't want to have any unexplained variance. So for the flow field agnostic version, we see that that 2 of our neural nets, neural network B and neural network C, happen to be performing the best. And then in the flow field sensitive case, our random forest ended up doing the best as well. We ended up sticking with neural network C as our, they're very close between neural network B and neural network C, but we wanted to choose the best one from each of these 2 separate corpus partitionings and take the best one from there. So for flow field agnostic, we went with neural network C, and for the flow field sensitive version, we went with the random forest. So here's how we did once we took these 2 best performing machine learning models and then plugged them into our oracles. So what this is a predicted speed up of our oracles. That is, when we took one of our 108 runs and said, are we going to get speed up, yes or no? If the answer was yes, if we were expecting to get speed up, we said, okay, that's great. Let's go and run it on Summit and see what we actually got. So ideally, in some ways, what we really want to have is to have all of our data align along these red lines. This red line indicates that our prediction is equal to our actually achieved speed up. However, we know there's going to be a little bit of error in any sort of model, and so in this case, what we would like to see happen is if we're off and our predicted speed up is not actually the same as our achieved speed up, we want to have a faster achieved speed up than what we predicted. So the goal is to have the dots be on the red line, but if they're not going to be on the red line, it would be great to have them above. And so you can kind of see the results visually here. So in kind of more of a tabular form, we also wanted to create some summary statistics. And initially, they don't look particularly impressive. If we consider all 108 runs and we see how well did we do for the defaults across all 108 runs, we're only getting about 5% speed up. With that being said, we noted that we could be, when we're a little pickier about which ones we're saying could possibly speed up, could possibly get speed up, we do actually achieve speed up. So this table right here, this table 3, is essentially a summarization of how many points are going to go above or below the red line that we saw before. Now that being said, what we also recognized is that a lot of our data that fell below that red line, that didn't quite achieve speed up, were runs that were really quick, kind of in just a few seconds range or before. And so we thought, well, in some ways, who cares if we're off in terms of speed up, which is a percentage for runs that run really quickly. What we care about are runs that are going to take a really long time, or heavy workloads that are going to take a lot of processing power. And so when we thresholded our runs by how long they took, what we noticed is that for runs that actually took quite a bit of time, our parameters did better. We started to get up to 20 or 23% for those runs, which took a minute or more than a minute to go once we consider them to be acceleratable. That is to say, once we go through, we examine, a workload, we say, yeah, we can do better than the defaults. For those cases, when we went and ran them, for those that ran for a while, we got about a 20% speed of the defaults. So to kind of contextualize this is, how well could you do? 20% is, better than nothing, but, it's still kind of modest. And so what we wanted to see is what were the available gains essentially. So we have this plot in the work, and what the gray points represent is some of our training data. And so what we're saying is for each of these, for each kind of line, as noted by for each horizontal line represents a number of configurations that correspond to a particular default in blue. And we're saying, so what we're getting at is we see a lot of gray, and we're saying, okay, the defaults actually work great for, whatever a combination of particles or batch sizes or whatnot, and kind of our training data that we try to really vary in order to cover the space. And turns out usually the defaults are pretty good. However, when we try to get our when we try to have some of our runs work through our oracles, through random forests and neural network, we were able to see that we actually got pretty good gains, even though in the wide range of our training data, which we thought covered the space pretty well, we're doing okay. I'll also note that this y-axis is ordered in terms of the workload. So you see that there's kind of maybe a little bit of a hint of a curve right here, and with these uppermost points indicating workloads that take a while, whereas these points down here are workloads that didn't take quite as long to run. So relative to the possibility, how well are we doing compared to chances, or how well are we doing compared to what's out there? I think we're doing pretty good in terms of the available gains that are still out there, because the defaults are already quite good for this algorithm. So just to kind of recap some of our research questions that we had. The first is, which machine learning technique can sufficiently model the performance of this parallelized-over-data particle advection algorithm? And the answer we concluded was neural networks and random forests. It beat the other models we considered. The other thing that we wanted to do to consider is how much speed up did our particle advection algorithm, parallelized-over-data particle advection algorithm, receive. And so the answer is, we received about a 5 to 20%, depending on, exactly how we're defining speed up and selecting data. That is, if we just consider, all on aggregate, more around 5%. But if we consider, scalable runs that, are going to take a while, closer to 20. And as we saw on the previous slide, we're thinking that compared to optimal settings, in the larger context, we're achieving, we're achieving things relative to the available gains. We're achieving most of the available gains still left. But this leads to kind of another question. Is it worth it at the end of the day? So one way that we thought about is how much compute node hours. So this workflow of of doing all this training and getting all this potential speed up, it's only beneficial if our production at the end of the day, our production gains outweigh the amount of time that it took to amass this training data and then train these models. So for our particular case, in order to amass our production data, which served as the basis for our training, we used about 400 compute node hours in Summit. And so by that kind of back of the envelope analysis, if we're able to achieve a 10% speed up over, 4,000 compute node hours, then we're going to break even. But there's this, question of how many compute node hours will we actually use? Are we going to have, 4,000 compute node hours over the course of this machine's lifetime? And so, the answer is a little bit application dependent. So if we're using streamline generations, on about 8 nodes for a dozen or so seconds, there would have to be just under 200,000 jobs in order to offset that. And we just don't think that's realistic. Now, that being said, there's a push to do some of this advection in kind of an in situ setting. So if we're thinking about an in situ setting, running a 30-second FDLE computation over 100 or so cycles, that would ultimately offset the training costs for some of these larger jobs. So once again, the answer is it's dependent on the advection workloads that are actually going to be used by practitioners. And we note that once we collect some data and knowing that this approach could work, perhaps it's possible for us to not have to amass so much training data. And so if training time is reduced, that's another factor that can motivate how this might be useful to implement. So thank you very much. I really appreciate your time and have a wonderful day.
Thank you very much, Sam, for this presentation. And now we are live here and you're ready to answer and ask questions. At the moment, I do not see any questions coming up, so I start myself. You just analyzed different machine learning techniques, basically which one is the best for your particular need, and you found out the champions who do the work best. That is what was it, random forest and neural networks. The question is, why them? Do you have any idea why these are the best techniques and the other techniques do not perform like this? Or did you completely treat them as black boxes?
Sure. We did treat them as black boxes in many ways. However, I think there can be some speculation or intuition as to why the random forests as well as the neural networks performed well. And one of the things that we noticed is that when we provided information about the underlying vector field or the underlying flow field, the random forest did better. And I think it's because when we did that made the manifold on which our data lived, through which the machine learning technique was learning, a little more blocky. Now, when we didn't include that, we were able to we tried really hard to have a really broad coverage. And I think that made our underlying training manifold a little smoother, which neural networks traditionally work, or in other contexts anyways, really succeed in learning from. So to recap, the answer to your question is we just treated them as black box models, but the results were perhaps not surprising now that we've done some. Now that we've done it, we see have a little bit of explanation.
All right, thank you. Are there further questions? No, I don't see any further questions. So that means we are done with the second paper. Thank you very much.
Thank you very much. I appreciate it.
And here we are again. Welcome to the third paper in this session. And this paper is called Scalable in Situ Computation of Lagrangian Representations via Local Flow Maps. And we have quite a number of authors here. Sudhanshu, Sane, Abhishek, Yenpure, Roxana, Bujack, Matthew Larsen, Ken Moreland, Chris Johnson, Christoph, Garth, and Hank Child. And Sudhanshu is going to give the presentation. Let's go.
Welcome to our presentation titled Scalable In Situ Computation of Lagrangian Representations via Local Flow Maps. My name is Sudhanshu Sane, and this work was done in collaboration with Abhishek Yenpure, Roxana Bujack, Matthew Larsen, Kenneth Moreland, Christoph Garth, Chris Johnson, and Hank Childs. Here is an outline of the presentation. We will start with a quick overview of the contents of this talk, followed by a discussion of in situ Lagrangian analysis, including our contribution in this work. We will then present results from the study we conducted, before concluding with the limitations, benefits, and directions for future work in this space. The contribution of this work is in the area of in situ Lagrangian analysis for time-varying vector field visualization. With the emergence of in situ processing, Lagrangian representations of time-varying vector fields have been increasingly researched in the past half-decade or so. In this work, we specifically consider the scalability of in situ Lagrangian analysis. Our study proposes and evaluates a communication-free model as a solution to address the scalability challenges that are important to address for viability in an in situ environment. We consider several different experiments in our study and present the performance, benefits, and limitations of the proposed approach. With that, let's take a closer look at in situ Lagrangian analysis. I want to start by motivating more clearly the need for this direction of research. I believe something many of us are familiar with is the fact that simulations running on supercomputers are constantly growing in resolution. However, while increased compute capability on supercomputers supports this growth, the I/O capacity on these machines has not kept pace. As a consequence, not all the data that is generated can be stored to disk, with strategies like temporal subsampling being frequently employed to reduce storage requirements. This in turn, however, can have adverse impact on post-hoc analysis. And this is particularly true for time-varying flow visualization, where many techniques are integration-based. Now, given the I/O bottleneck challenge, in situ processing is becoming an increasingly important solution to enable analysis of large-scale simulation data, and it offers new opportunities to enable time-varying flow visualization. Specifically, in relation to this talk, Lagrangian representations can be computed accurately using in situ processing by operating on the full spatiotemporal resolution of the simulation data. So let's take a step back and answer, what is a Lagrangian representation? In a practical sense, a Lagrangian representation of a time-varying vector field consists of sets of particle trajectories. We also refer to this as the flow map. The particle trajectories that form the Lagrangian representation are computed using in situ processing and can be interpolated post-hoc to reconstruct the flow field behavior. Note that since the particle trajectories are computed using in situ processing, these trajectories can be considered as accurate. The figure here gives an overview of the two phases of Lagrangian analysis, the in situ phase and the post-hoc phase. The legend at the bottom shows which particle trajectories belong to which phase. In the plot, there is a horizontal time axis going from left to right and a vertical spatial axis labeled x. In this example, the in situ phase uses uniform seed placement and extracts flow maps over temporally non-overlapping intervals. These intervals are labeled as interval 1 and interval 2 in the plot. In interval 1, from t0 to t1, the flow map consists of particles x0, x1, and x2. During interval 2, from t1 to t2, the flow map consists of particles x3, x4, and x5. Once these flow maps are computed and stored to disk, new particle trajectories, in this example the red trajectory, can be calculated by interpolating the extracted data. So the red particle can interpolate its end location using particles x1 and x2 over the first interval and particles x3 and x4 over the second interval. There have been several works advancing various aspects of in situ Lagrangian analysis. A few works have proposed in situ strategies to extract flow maps, essentially sampling techniques. These have considered uniform sampling with fixed interval lengths, using long trajectories with multiple points stored along the curve, and distribution-guided sampling as well. Considering the latter two were only demonstrated on a single node, none of these works have truly addressed the scalability of performing this in situ analysis task. There have been several works that have considered how to use the flow map data once it is extracted. This has included using curve fitting to improve the aesthetics of reconstructed trajectories, theoretical error analysis works to identify causes of error when interpolating Lagrangian representations. Some works have considered search structures and multi-resolution techniques to improve the interactivity of visualization systems using flow maps. And most recently, there has been work using machine learning to upsample FTLE visualizations generated by low-resolution flow maps. Overall, there has been progress in our understanding of the paradigm as a whole and how we can use it for analysis. In this talk, we will be focusing on the in situ phase and specifically scalability. Computing a Lagrangian representation in situ typically can involve distributed memory particle advection. Now, a well-known and likely the most significant challenge associated with distributed memory particle advection is scalability. And this poor scalability is due to the frequent and large amount of communication required between processors as particles continue trajectory integration across rank domain boundaries. In the context of post-hoc analysis, several solutions have been explored. These strategies typically involve identifying ways in which communication can be reduced or eliminated. When using a parallelize over particles strategy, techniques have moved or duplicated data between processors, or they have adopted on-demand data loading. When using a parallelize over data strategy, data layout modification using pre-processing strategies seems to be a frequently explored option. Many of these works have also only considered distributed memory particle advection for single time slices of vector fields. Overall, these solutions are not directly applicable to the problem of performing in situ distributed memory particle advection. Besides operating in a time division setting with the simulation code, distributed memory particle advection performed in situ to compute a Lagrangian flow map has a few constraints that are important to note. In our paper, we've got a more exhaustive comparison between the requirements for in situ and post-hoc distributed memory particle advection. But here I just want to touch upon those that I view as the most relevant. Firstly, we are always considering a time-varying vector field. Taking into account the memory constraints that an in situ task is likely operating under, at any given time, only a limited number of time slices of the vector field can be available. These constraints also dictate the need for communication to occur every single cycle. Whereas in a post-hoc setting, there have been works that delay communication until all the particles reach the boundary. This, however, does not appear to be possible when performing particle advection in situ. The next points are spatial decomposition and data access. When operating in situ, the domain decomposition is determined by the simulation, and typically an in situ analysis task can only access the data of the rank it is operating on. Thus, using techniques like pre-processing or on-demand loading that have been explored for post-hoc analysis don't seem viable in this context. The last point I want to address is not so much of a constraint, but certainly a difference between post-hoc analysis and in situ processing. It's the objective of the task. Our goal here is to store a representation of the vector field. This is different from a post-hoc setting where analysis or visualization are the objectives. So with this work, we make two contributions. First, we provide a scalability study of distributed memory Lagrangian flow map computation using GPUs for particle advection. Second, we provide an evaluation of a proposed performance optimization, computing local Lagrangian flow maps. As a baseline, we use the most commonly used approach. I will refer to this as Lagrangian distributed. Here, sampling is performed using a uniform seed placement and a fixed interval. We only store the current location and validity of each particle in memory. We require communication between ranks every cycle to determine if a particle exchange is required or not. And lastly, we store only the end location and validity for each particle. Our proposed approach is a communication-free model. I will refer to this as Lagrangian local. The sampling, in-memory representation, and storage are the same as the baseline. The big difference here is the approach uses no communication. If a particle reaches the boundary of a rank-specific domain before the end of the storage interval, and it requires communication to continue integration of the trajectory, we terminate and discard the particle. While such an approach introduces an accuracy performance trade-off, there are a few reasons we believe it could be effective. First, prior Lagrangian analysis works have shown that you don't lose a lot of accuracy when reducing the number of particles that form the flow map. That indicates to us that if we start with a sufficiently high number of particles, we might still be able to encode the behavior of the vector field relatively well. Second, we believe if not too many particles are discarded, spatial coherence in the domain can help reconstruct the lost data without too much error. The big benefit of such an approach is not requiring any communication or synchronization between ranks in situ. This has the potential to reduce the execution time at scale, remove any dependence on domain decomposition or rank placement, and could buy more time for advanced in situ sampling strategies. With respect to reconstruction once flow maps are extracted, we used the standard approach of performing a Delaunay triangulation and using barycentric coordinate interpolation to calculate new particle trajectories. For example, here we have the triangulation over the flow map extracted using Lagrangian distributed. Post hoc, a new particle would identify which cell it is contained within and use the end locations of the particles that form the cell to interpolate its own end or next location. The same approach is used for Lagrangian local. Although cells in the Delaunay triangulation where particles have been discarded will have a larger circumradius. Lastly, I want to share some implementation details and the runtime environment we used. We used the Alpine Ascent in situ infrastructure to couple with simulation codes or create the in situ workflows we used in our experiments. We used the worklets from the VTKM library for particle advection using GPUs. And in the reconstruction phase, we used the Seagull library to perform the Delaunay triangulation. We conducted all our in situ Lagrangian flow map computation experiments on the Summit supercomputer at the Oak Ridge National Laboratory. Our study considered 4 datasets: Cloverleaf 3D, ABC Flow, a NIX test executable, and the JetFlow dataset. Our experiments informed scalability via a weak scaling study and efficacy via evaluations of reconstruction accuracy, where parameters such as degree of domain decomposition, storage interval, and number of flow map samples are varied. Our evaluation considered the execution time for particle advection and communication. And our reconstruction accuracy is presented as a percentage of grid cell side. That is, what percentage of the grid cell side is our result from the ground truth. We present our quantitative results using violin plots, and we derived FTLE visualizations from the flow maps for a qualitative comparison. I want to point out that all the violin plots in the results that follow are the error of reconstructing the discarded particle trajectories only. This allowed us to isolate the error in regions where particles have been discarded. Further including reconstruction of particle trajectories throughout the domain would skew the results, since in all of our experiments, over 80% of particles remained within the rank domain and were stored. We expect these regions to support high accuracy reconstruction. In this presentation, we present the outcomes of the majority of our experiments and analysis. I encourage you to refer to the paper for all the experiment results and analysis. Before going through the results, I want to give you an idea of the order in which they will be presented. we will first look at the execution time of our weak scaling study using the Cloverleaf 3D dataset, and then the execution time when using a fixed scale and varying workload for the other datasets. Next, we will look at reconstruction accuracy results for the flow maps extracted from the weak scaling study and the fixed scale studies. Last, we will look at a study that considers varying domain decomposition for a fixed grid size, and how varying the number of particles and storage interval play a role in reconstruction accuracy in this context. Beginning with the results from our weak scaling study, the plot on the right shows the number of MPI ranks on the x-axis and the average time per step on the y-axis. The red curve is the result of the Lagrangian local tests, and the black curve, the result for the Lagrangian distributed tests. We conducted experiments that used up to 2048 MPI ranks across 512 compute nodes. Here, each rank used a single GPU. That is, we used a total of 2048 GPUs in our largest experiment. Each rank operated on a 64-cube domain, and we ran the experiment for 500 cycles. Thus, our smallest grid was 81 cubed and the largest grid was 812 cubed. We note that as the simulation resolution increased, the step size taken decreased. This is expected behavior for most simulation codes. For each test, we used one particle for every 8 grid points. So we have approximately 32,000 particles per rank. We reset the particles after every 25 cycles. Lagrangian local terminated between 2 to 5% of particles on average. We observed a 4x speedup on average across all the tests, and we expect this speedup to increase at larger scale or if we use a faster particle advection kernel. I want to point out the sawtooth nature of the line curves in the plot are a result of alternating between 4 and 6 ranks per compute node. For particle advection, we found the execution time is less when only 4 GPUs are operating on a compute node rather than 6, since memory is shared by these GPUs. For communication, we observed the opposite, with execution time being lesser if there were 6 ranks on a compute node rather than 4, since it could benefit from on-node MPI communication optimizations. Here we have the results for our experiments that considered a fixed scale of 64 ranks across 16 compute nodes for the remaining datasets. Starting from the left, the chart shows the results for the ABC dataset in the first 3 columns, the NIX dataset in the next 2, and the JET dataset in the 4 columns on the right. The x-axis shows the total number of particles that were used to form the Lagrangian flow map, whereas the y-axis shows the average time required per step. We observed different speedups for each dataset, 2.8x for ABC, 5.2x for NIX, and 3.9x for JET. We used box plots to show the variation in time required, and it is observable that Lagrangian distributed tests show significant variance in many cases. In contrast, Lagrangian local only had one instance where execution time varied significantly. Moving on to the reconstruction accuracy results, the violin plot shown here is the reconstruction accuracy for the discarded trajectories from 8 of the weak scaling experiments using the Cloverleaf 3D dataset. The x-axis labels the tests T1 through T8, where T1 is the lowest resolution and T8 is the highest. The y-axis shows the reconstruction error where our metric is the percentage of grid cell side a particle is away from the ground truth. We can see that as the scale increased, for our selected configuration of a storage interval of 25 and 1 particle for every 8 grid points, the reconstruction accuracy did not increase significantly. I want to point out once again that as the simulation increased, the step size decreased. Thus, although the domain was decomposed further, particles took smaller steps as well. We did not observe a significant increase in percentage of particles discarded as the simulation resolution increases, with all our tests showing between 2 and 5% of particles being discarded. For these discarded trajectories, we found that the majority of the particles were reconstructed under 50% of a grid cell side away from the ground truth. For the ABC dataset, we used a 256 cube grid over 400 cycles and considered 3 options for storage interval and data reduction. The details of these tests are available in this table. As expected, we can see that as the storage interval increases, the number of particles discarded increases as well. The violin plot for reconstruction error for these tests showed the increase in error as the number of particles used to sample the domain decreases and the storage interval increases. That said, most particles are reconstructed fairly accurately and are within a grid cell side of the ground truth. The FTLE visualizations on the right compared the ground truth FTLE to the FTLE derived using a flow map from test T6. In this experiment, almost 10% of the particles were discarded. Although reconstruction near extrema is similar to the ground truth, the FTLE field is overestimated in other regions. For the next dataset, we used a 128 cube grid over 400 cycles and considered 4 options for storage interval and 2 data reduction options. The details of these tests are available in the table. This dataset had the largest number of particles discarded among all our experiments. The violin plot for reconstruction error for these tests showed the increase in error as the number of particles used to sample the domain decreases, and the storage interval increases. In this case, certain tests using either a large storage interval or a reduced number of particles in the flow map show reconstruction error can be over a single grid cell side away from the ground truth. That said, for multiple configurations, the majority of particles were reconstructed within a single grid cell side of the ground truth. For example, test T1, T2, T5, and T6 show relatively accurate flow map reconstruction. The FTLE visualization on the right compares the ground truth FTLE to the FTLE derived using the flow map from test T1 and T3. The ground truth has an FTLE computed over 40 cycles. T3 had an interval of 40, whereas T1 had an interval of 10, so we needed to interpolate 4 intervals to derive the FTLE field. In the visualization of a slice of the FTLE field, a similar structure appears. Although, when you visualize multiple isocontours, you can see the noise that gets introduced locally into the T1 reconstruction due to error propagation. In comparison, T3, which requires a quarter of the data of T1, reconstruct the FTLE without as much noise and is quite similar to the ground truth. For the JET dataset, we used a 128 by 128 by 256 grid over 300 cycles and considered 2 options for storage interval and 4 options for data reduction. The details of these tests are available in the table. We considered data reduction options up to 1:64, that is, 1 particle for every 64 grid points. The violin plot for reconstruction error for these tests again show the increase in error as the number of particles used to sample the domain decreases, and the storage interval increases. In particular, T6 and T8 show poor reconstruction, whereas T1, T2, T3, and T5 have the majority of particles being reconstructed within one grid cell side of the ground truth. The FTLE visualization on the right compares the ground truth FTLE to the FTLE field derived using a flow map from test T1 and T3. This allows us to see the impact of reducing the resolution of the flow map used to derive the FTLE field. Overall, the main structure in the FTLE field is preserved, although there are some artifacts that are visible as well. The last set of tests are related to the degree of domain decomposition. We use the Cloverleaf 3D dataset for this set of tests. Here, we compare the accuracy of Lagrangian local and Lagrangian distributed to the ground truth. We measure the error of path lines over 500 cycles in this case. We used a fixed grid size of 64 cubed, and we decomposed this grid into 1, 8, or 32 blocks. Essentially, we investigate how the error is impacted as the number of boundaries within the domain increases. That said, the experiment configurations decomposing a 64 cubed grid into 8 blocks and 32 blocks tests an extreme case. We would expect simulations to have at least a 64 cubed grid per rank in a practical setting. We considered 3 data reduction factors, these are the columns, and we considered 3 storage intervals, these are the rows. We color a cell by the average error of interpolated locations. The results for Lagrangian local are on top, and Lagrangian distributed are below. There are 2 key observations here. First, both Lagrangian local and Lagrangian distributed show error as the number of particles used to form the flow map decrease. That said, the error is not very high, with the average error still being within a single grid cell side of the ground truth. The second key observation is the configurations which make Lagrangian local most vulnerable. These are configurations where there are very few particles that form the flow map and there is a high degree of domain decomposition. This is the rightmost column in the table. It is also worth noting that when the domain decomposition is only 8 blocks, Lagrangian local provided similar accuracy to Lagrangian distributed. This work contributed a scalability study as well as an evaluation of a simple communication-free model to extract Lagrangian flow maps in situ. The benefits of this approach were reduced execution time and improved scalability. We also found that it led to greater predictability of in situ analysis costs, which we believe is important at scale. Our study also showed that in many cases, the flow maps could be reconstructed accurately when a high number of particles were used to form the flow map and the storage interval was such that only a few particles were discarded. A limitation of the work is that it can be vulnerable to conditions where too few particles form the flow map. This could either be due to a long storage interval or too few particles initially, that is, a high data reduction is being used. This, as a consequence, can impact analysis and result in regions potentially being misrepresented. These limitations, though, we believe can be addressed through future work, and there are several practical use cases for Lagrangian analysis in practice today that could benefit from flow maps being extracted using a communication-free model. Future work, specifically adaptively determining appropriate storage intervals, is applicable to all Lagrangian representations. Further, the development of post-hoc reconstruction schemes that can efficiently interpolate more complex Lagrangian representations, such as those with arbitrary start and stop times, would also benefit the community. With that, I will conclude the presentation, and I would like to thank you for your attention.
Thank you very much, Sudhanshu, for this presentation. I enjoyed a lot, and we are ready to take questions. Up to now, I don't see any questions popping up, so it's again my pleasure to start with questions. You integrate your particles and you throw away the particles that are crossing the boundary to another node, and then the surviving particle you do the Delaunay triangulation, and then you have your field actually. I was wondering if with these reconstructed particles, if you observe a varying density of these particles, something towards the middle of the blocks, there's a higher particle density, and towards the boundary of the blocks, there's a lower density, because at these areas, there's a higher chance of a particle to be killed. Could you observe such different particle densities?
Yeah, I think those densities do differ in the stored flow map. And I think that error shows in the FTLE visualizations when you look at them. If you do these isocontours or isolines through it, when you visualize the pseudo color plot, it's not as visible. But when you visualize isolines going through a slice, you can see that at the boundaries, there'll be some distortion. And so what we found was when you have a single interval, whether it's 10 time steps, 40 time steps, 50 time steps, that error gets still limited to that small boundary region. We found that when you have multiple such intervals interpolated one after another, then that error can result in noise in the local region near those boundaries. So yes, there is some amount of noise that gets introduced, but it also depends on what the data set is like, how many particles were terminated. The number of particles terminated across the domain was not consistent. There were some regions which would have more particles terminated depending on likely the velocity in that area of the vector field versus other regions where we noticed maybe no particles were terminated, but it was relatively, let's say, calm at that moment.
I see. Thank you. You have already shown in the paper that the results of this communication-free approach pretty much depend on the characteristics of the data set.
Yes.
How can you imagine a hypothetical data set where your approach works perfectly with no error, absolutely perfectly, and also the opposite? Can you think of a data set where your approach works not at all, gives totally crap, and is totally the worst thing what you can do? Can you think about these extreme data sets?
Yeah, I think the perfectly case, we've tested it on some simulation codes, like for example, the NIX simulation code, which is a cosmology, self-gravitating gas dynamics code. We saw performance was actually really good on that. Another data set we saw performance was really good on was a seismology simulation where waves were propagating from an epicenter. And so the direction was relatively the same for the entire simulation, just in waves, transient waves. And so Lagrangian particles are really good at capturing that behavior. Where it would be really bad, we actually noticed that if you have the jet data set in our tests, in our examples in the paper, we saw that the performance wasn't good in some regions, particularly where the velocity field was very high, where the jet was. And so I imagine that is a situation where you would need either a very small storage interval or need to basically be monitoring how many particles you're discarding from certain blocks. And so that would be an interesting way to go forward as to having a cap on that so that you can know when you should stop and reset your particles. Or another way to possibly address any such shortcomings would be to then start storing end locations and having a more fluid sampling strategy where you can add new particles as needed and still terminate them at the boundary. I do think that operating or generating local flow maps is definitely useful in that it provides inherent scalability in its design. But like you said, the shortcoming of terminating a particle in certain cases, certain vector fields might have behaviors where that could be, it's possible to design a vector field where you can say all particles leave randomly. So yeah, there could obviously be downsides, but in most practical cases, with the number of steps between storing data and the step sizes that particles take, we think that the number of particles being discarded would still stay relatively small.
Yes, I would expect that probably the speed, the magnitude of the velocity or the average magnitude might be a key factor. Slow flow, good for your approach. Fast flow, bad for your approach.
Yeah.
It might, did you think about, based on this measure, some recommendation when your approach is worth before actually carrying it out?
No, we did not evaluate any field-specific heuristics in this work. I do think that with Lagrangian representations in general, understanding the right temporal intervals is important and pretty much remains unsolved at this moment as to what the right sampling frequency should be in the temporal axis. And the challenging part about it is that it would not only vary, it's per particle, essentially. It wouldn't be for the whole domain. So it would actually need to be a strategy where you can determine on a per particle basis when is the right time to start, when is the right time to stop. And so again, that's the idea where I think that we should move towards as to when is the right time to store information along a particle trajectory rather than in a block specific setting.
All right, thanks a lot, Sudhanshu.
Yeah, thank you for your questions.
Are there further questions? I do not see any questions now. That means we are at the end of the session. So let's thank all the speakers again. Let's clap hand. Let's continue the discussion in Discord, and then we are done with the session. Thanks a lot for all the speakers. Thank you.